Okay, I missed to have it recorded. So here it is now. So the first part of this review will be the terms that we have covered in process control, and some I have taken from other sources. So we have here a plant is an arrangement of processing units integrated with one another in a systematic and rational manner. So the control system is the arrangement of the physical components connected or related in such a manner as to command, direct, or regulate itself or another system dynamically or actively. So it may not only be able to regulate another system, but even itself. So it's a continuous active process of regulation. So that's your control system that does that. Your input variables are considered as the stimulus or a form of excitation or command applied to a control system, typically from an external energy source, usually in order to produce a specified response for such a control system. So another definition, form of definition for the input variables. For the output variables, these are the actual response obtained from your control system. So it may or may not be equal to the specified response implied by the input. Now we have what we call the manipulated or adjustable variable. So these variables are used to maintain the controlled variable as its set point. So as the term manipulated, so they are the variables that we can adjust or manipulate. That way, we can make sure that our control variable may be not as equal as what is set for it, but rather comparable to or near to the value of the set point. Now we have the disturbances or the upsets. These are any variable that can cause the control variable to deviate away from the set point. So anything that will alter the value of our control variable, that is our upset or disturbance. Kindly check if you are muted. And check as well if you can see what is being projected. So for the controlled variable, so this is the variable that must be maintained or controlled at some desired value. The set point is the desired value of the controlled variable. Now the term bandwidth, you have encountered this towards the latter end of the course. So the bandwidth of a system is a frequency response measure of how well the system responds to or filters variation or frequencies in the input signal, how well it filters frequencies or how well it responds to variations in the input signal is a measure of its bandwidth or the system's bandwidth. Now we have words connected to control, terms connected to control such as analog or digital terms. So an analog signal is dependent on a continuum of values of the independent variable t, and it is called a continuous time signal, or more generally it's referred to a continuous data signal or an analog signal. So continuous time signal, continuous data signal are all synonymous to the analog signal. The common form of the signals that are now being transmitted from one source to another is what we call as the digital signal. So defined at or at of interest at only distinct or discrete instance of independent variable time upon which it depends and is called, so a digital signal is also referred to a discrete time signal, a discrete data, a sample data signal. So these three are synonymous to the digital signal: discrete time, discrete data, or a sample data signal. Now, feed-forward control is a type of control which measures the disturbances and compensates for them before the control variable even deviates from the set point. If applied correctly, the control variable will not deviate from the set point. So it's an anticipative control in which before the effect of the disturbance or upset is felt by your system, it's able to make your system compensate for it. That way, no changes in the control variable will happen. Now we have the block diagram. So it's a shorthand pictorial representation of the cause and effect relationship between the output and the input of a physical system. So a shorthand pictorial representation, that's your block diagram. Now we have this term sampler. A sampler is a device that converts a continuous time signal into a discrete time signal. Now we have what we call a hold or a data hold, which is a device that converts the discrete time output of a sampler into a particular kind of continuous or analog signal. Continuous time or analog signal. So the opposite of the sampler is the hold. So it converts your discrete data to continuous data. Now, the transducer is a term that was already introduced to you in the start of the semester, last semester. Is a device that converts energy form into another. So a transducer converts a signal in the form, let's say, of a physical signal into an electrical signal. So we cannot, your control system cannot interpret physical signals. What it can interpret are only signals like in the form of current or voltages. So the one responsible in converting such is the transducer. Now we have the potentiometer as a specific transducer which converts a mechanical position into an electric voltage. Now, another term of the test input is what we call as the stimulus. It's an externally exogenously introduced input signal affecting your controlled output, the stimulus or the test input. Now, a disturbance, in some reference books, it's referred to as the end because it's also referred to or could be also connected to the phrase noise input. Is an undesired stimulus. As such, it's a disturbance or input signal affecting the value of the controlled output. So in old books, it's simply referred to as the noise or the disturbance, a negative or undesired stimulus. Now we have what we call an on-off controller. So a two-position binary controller and has only two positive values at its output U. Now it only depends on the input E to the controller. The E here is the error. Now we have also discussed the proportional controller has an output U proportional to its input E. That is your U is equal to K sub PE, where your K is a proportional constant. Now, this is another definition that I got from a different review material regarding the definition of a proportional controller. And we cannot expect that the way it's being asked later on when you take your exams, your board exams, will be similar as the one that is phrased in Kauhanor or any books that you have used so far. So I am trying to give you different definitions of this term. That way you will know that they mean the same as those that you have been acquainted of. Now, a derivative controller represented as D has an output proportional to the derivative of its input E. That is your U is equal to the K sub D times the derivative of E dt with respect to time. Now, where K sub D is a proportional constant again. So you have here the time derivative of the error, dE dt, multiplied to the K sub D, which is a proportionality constant. Now we have the integral controller. This one has an output U proportional to the integral of the error. That is, U is equal to K times the integral of the error, where K is a proportional constant again. So These are the three types of controller that we have discussed. Somehow, the definitions here have some similarities to the ones that were discussed in Kauhanor. Now, we have servo mechanism here is a power amplifying feedback control system in which the controlled variable C is mechanical position or a time derivative of position such as velocity or acceleration. So an automobile power steering apparatus is an example of this servo mechanism. So all our automobiles that have power steering apparatus is operating on this servo mechanism system. So a power amplifying feedback control. It's amplifying your motion when you try to move the steering wheel. That way, at just very small movement of the steering wheel, the wheel of your car already moves, shall I say, to a greater extent compared to non-power steering power mechanisms. So gina-amplify niya ang movement. That way you need not really do a lot of movements with respect to the steering wheel. That is so that your car will be steered in the direction that you want it to position itself or go. Now we have a regulator. So we have discussed these terms actually, servo and regulator problems, but they are defined differently. So a regulator or a regulating system is a feedback control system also, in which the reference input or command is constant for long periods of time, often for the entire time interval during which the system is operational. So the thing that you need to understand here is that the reference input or command is constant for long periods of time. So such an input is often called as the set point. Now, the overshoot is a term that was introduced to you when we were discussing higher order system, specifically the second order higher order system. So the overshoot of the second order system in response to a step input is the difference between the maximum value attained by the output and the steady state solution. So this is easily understood if you see the oscillatory nature of the response curve of our second order system. So we speak of the overshoot in layman's term as how much did your output exceeded the steady state response. But another way of defining it is the one that you see in this bullet. Now, there are terms poles. I'm sure some of you have done your researches in the internet, and there are terms that such as zeros or poles of the function. So the poles of a transfer function are the values of s for which the g of s or the transfer function will be infinity. Poles. So what values of s will you substitute to your transfer functions in such a way that it will be infinity? So very simple. If you have a rational expression, what will make it infinity is that the denominator of that expression, which is rational, such as in the case of our transfer function, should be set to 0. This corresponding roots of the polynomial in the denominator of your transfer function corresponds to the poles of your transfer function, because it will make the value of your transfer function infinity. So you just need to equate that polynomial in the denominator of the transfer function. Everything, your calculator can do that for you as long as it does not go beyond, I think, third degree. As for the zeros of the transfer function, these are the values of for which your g of s is 0. So you just simply equate your g of s expression to 0. So automatically your denominator will be cross-multiplied to the 0 value. So in this case, it's this time the numerator that you will be equating to 0. The roots of the numerator of your transfer function will be the zeros of your transfer function. If the poles will make the denominator of your transfer function 0, the zeros of the function will make the numerator of your transfer function 0. Okay? Now, gain margin. So it's the additional gain that makes the system on the verge of instability. that margin, it's actually given in the form of a percentage added to the actual gain of the system that is stable, in which your system will be in the verge of being unstable already. So that's the gain margin. The phase margin is the additional phase lag that makes the system on the verge of instability. An added value to your phase lag or your zeta that will make your system unstable is your phase margin. Now, as to the offset, we know that it is the steady state value of the error, or the difference of your new steady state value from the set point. That's your offset. Okay? Now, feel free to interrupt me if you have any questions. So non-regulation and regulation terms you have encountered already. A condition where the response of the system grows without limit, non-regulation. So growing without limit for a sustained change in input. When we speak of regulation, a condition for systems that have a limited response for a sustained change in input. Then we have terms like interacting systems and non-interacting systems. Flow through a resistance in between tanks is dependent on the difference between the levels of the first and second tank. So they are said to be interacting. And the irony of the term interacting, if you can still recall it, is that it is using the term that the second tank is loading the first. We don't say, it's the usual case, we say the previous tank is loading the second tank. But in the case of interacting system, it's actually the next tank that is said to be loading the first. So it affects the response of the previous tank based on this. Okay? Non-interaction is simpler because the variation in the level of the succeeding tank does not affect whatsoever the transient response of the previous tank. The damping coefficient, so this is the measure of the degree of damping in the oscillatory characteristic of the response of a second order system. And this is our zeta, the damping coefficient. The rise time, the time required for the response of a second order system to reach its ultimate value. So the time required. So the very first time actually required for your response to reach its ultimate value. When you answer for the response time, I have checked your quiz. The response time, I'm not sure if there's one who answered in the form of a range. When we speak of response time, the answer is range. Because if you notice, it's the time required for the response of the second order system to come within plus minus 5% of its ultimate value and remain there. So plus minus 5%. So meaning it could either be 95% of the ultimate value or 105% of that. So unless otherwise your system already stabilized, you have a horizontal line already for its graph, then your answer for the response time should be in the form of a range of values from 95% to 105%. Now, transportation lag, so a phenomenon often encountered in flow systems, which is also known as the dead time or the distance velocity lag. The load, the change in any variable that may cause the control variable of the process to change. The change in any variable, not just in the input to your system, that may cause your control variable to change is preload. We have negative feedback and we have positive feedback. So negative feedback is the usual case. Ensures that the difference in the measured variable and set point is used to adjust the control element so as to reduce the error. Take note, class, that ensures that the difference in the measured variable, not the actual output, but only the sensed output, and set point is used to adjust the control element so as to reduce the error. This is the usual case. For positive feedback, it adds the measured variable to the set point, which makes any control system unstable. This control arises in more complex system, but it does, though we may not fully comprehend why will you add your measured variable to the set point, but in complex system, they do that. Okay, so far our focus in process control was so much more on the negative feedback. For servo mechanism, the set point is being changed in accordance with the desired variation in the control variable. This means that the engineers that designed the process has already in mind, or has part of the objective, stated in the objective, the range of values of the control variable. So what they do, they change the set point that way their control variable should not be out of range, or desired range of values for the control variable. So in that case, they're not getting the difference of the set point and the measured value, nor they added the measured value to the set point, but it's the set point that they change based on the desired range of value of the control variable. Now we're on the last part on the term. So when you speak of the regulator problem, this maintains the control variable in spite of the changes in the load, or in spite of the loads in which your system is subjected to. So this is the usual case, the regulator problem. Now we have the term reset rate, and this term was discussed when we were on controllers, type of controllers. So this is the reciprocal of the integral time, or the time integral. Okay, that's the reset rate. Now, our control systems can either be open loop or closed loop, or the other term of which is feedback. So the controller in the open loop system is disconnected from the process. That is, the controller is not making any decision on how to maintain the control variable at set point. The action taken by the controller does not affect the measurement, or vice versa. The measurement does not affect any action that the controller decides to do or equates the control element to do, because it's disconnected. Your measured value is disconnected to the controller. The closed loop, or the feedback loop, is that the controller is connected to the process, comparing the set point to the control variable and determining the appropriate corrective action to do to return the control variable to its value. Now, another definition, you already have here open loop, but this time I took it from a different source. So open loop, they have this ability to perform accurately as determined by their degree of calibration. So they can perform accurately as long as they are calibrated. So to calibrate means to establish or re-establish the input-output relation to obtain desired system accuracy. These open loop systems are not usually troubled with problem instability. Whereas on the other hand, when we speak of the closed loop system, they are also called feedback control systems. Feedback permits the output to be compared with the input to the system, so that the feedback appropriate control action may be formed as a function of input and output. Now, the four basic elements of your control system, you know, it's the sensor, the transmitter, the controller, and the final control element. Now, these are the three basic operations your control system must perform, acronym MAD. So measure, decide, and act. So this was covered as well as SEM. As to types of feedback systems, we know we have positive feedback and we have negative feedback, but they can also be categorized as linear or non-linear, time invariant, or time varying systems. So linear or non-linear feedback systems. So strictly speaking, linear systems do not exist in practice. So linear systems are idealized models which are used as basis for analyzing non-linear systems. Just like when you recall your kinetics, then you use the ideal reactor models to come up with the design of real reactors in the industries. So when we speak of time invariant or time varying systems, so when the parameters of a control systems are stationary with respect to time during operation of the system is called to be time invariant. So meaning time derivatives of your process variables are zero. They don't vary with time. So in practice, most systems contain elements that drifts or vary with time. So in the real industry setting, there is no such thing as a time, shall I say, invariant system, wherein process variables remain constant over long periods of time. They will always have, after some time, a drifting or a varying in their values. Continuous data control system. So a continuous data system is one in which the signals at various parts of the system are all continuous time variables or functions of continuous time variable. When we speak of sample data and digital control systems, so sample data and digital systems refer from continuous data systems, and that the signals at one or more points of the system are in the form of either a pulse train or a digital code. Now, usually sample data systems refer to a more general class of system where signals are in the form of pulse data, whereas the digital control system refers to the use of a digital computer or controller in the system. So this is more on the field of, this is more focused on that field of controllers already. Now, regulator and servo mechanism being contrasted here. So a regulator differs from a servo mechanism in that the primary function of a regulator is usually to maintain a constant controlled output. A constant controlled output, while that of a servo mechanism is most often to cause the output of the system to follow a varying input. One is making it constant, while the other one, the servo mechanism, makes it follow the corresponding changes in the input that is varying. That's servo mechanism. Now, for the formulas, you may start already writing your formulas in your index cards. That way, from time to time, you can simply, even if you're eating or you're doing something, you can scan on them. Okay, you have here the Laplace transforms of the functions you see here on the left. So you have the unit step, you have the exponential function, you have the unit ramp, the sine, the cosine, the unit impulse, the polynomial function, and the damped sine and the damped cosine. Please take note that we don't use the shifted term here, but in controls, we use the term damping. I think you fully know already their Laplace transforms by now. So just acquaint yourselves again on the terms connected to these particular expressions of the functions you have in the second column. As for Laplace of derivatives, of course, you cannot determine the transfer function of a system that you first and foremost learned how to model if you do not know Laplace transforms of derivatives. So there is a pattern in this one, but what I wrote in here is just the Laplace transform of the first derivative. Okay, we start with s raised to a power equivalent to the order of the given derivative. It's being multiplied to the function of s. The rest of the terms in that particular equation will be s reducing in power and f of 0 starting with f of 0 down to the derivative of f of 0, which is of order 1 less than the given order of the derivative. For the Laplace transform of an integral, this is only applicable for functions in which the integral is being evaluated from 0 to t. And another application of this, if you want to determine the function of t for a given function of s in which you have 1 over s raised to a certain power. So you can set aside the 1 over s. So depending on the power of that, let's say you have 1 over s squared, or 1 over s cubed, or 1 over s to the fourth, the order of the power of the s tells you how many times you will integrate the inverse Laplace of this given function of s, the one that I am circling. So you don't need to do method of partial fractions in that sense, and it makes the process less tedious. However, of course, if you have a problem with integration, that's some challenge for some. So it depends on which particular process are you more comfortable with. The initial value theorem and the final value theorem, if I may say, is very, very useful in your case. Because whenever you are asked to find the initial value of the function, like the f of 0, y of 0, and the final value of the function, either y of infinity or f of infinity, this will really be very beneficial in the sense that there is no need for you to invert your given y of s. That way you can substitute 0 and infinity for the time, but directly process the initial value and the final value of your function by using the formula, the limit of the product of y of s with s. You evaluate the limit as s approaches infinity for initial value of the function, and you evaluate the limit of sy of s when s approaches 0. Okay, these two are very, very important. They make the process less tedious, okay, in determining values of the function. We say the function is translated, so you could see here translation of the function. If your function has a constant being subtracted from its variable. So this is the usual way. This is rather the way we write it in controls. But in pure math, we write it as f of t minus a. And this is the consequence of this is the second shifting property of Laplace, wherein you have e raised to minus as then in advanced engineering mathematics times the function of s. We call this in controls as translation of function. The translation of the transform, rather this is the translation of the function, not the transform. The translation of the transform is the first shifting property, wherein the transform itself or the Laplace transform itself of your function is the one that is being translated. As to what is being translated, it is the s in that particular function of s that is being translated. Laplace transform of the pulse. So this is the duration of the pulse, h, and this is the height of the pulse, 1 over h. So if you have the illustration of the pulse, this may change. So it depends on what's your representation of the magnitude of the pulse. So this 1 over h actually is the magnitude of the pulse, and the h is the duration of the pulse. So you need not derive this again as long as you understand that. So again, 1 over h is the magnitude of the pulse. H is the duration of the pulse. For the Laplace transform of the unit impulse function, so you have it as 1. Okay, if it's not unit, so if the magnitude of your impulse function is other than 1, then the Laplace transform of that will be the magnitude of your function itself. Okay, in here you have the Laplace transform of a unit step function. You know this already. The Laplace transform of a ramp function. The Laplace transform of a sine function of magnitude a. So this is the magnitude of your sine function. So you have A omega S squared plus omega squared. I place in here that the steady state gain of your system is the K value taken from the limit of the G of S as S approaches 0. So take note, your transfer function, you take the limit of that, substitute the value of, you take the limit of that as S approaches 0. And that would be the steady state gain of your system. Oftentimes, this one, as I have pointed out in our discussion, is the constant that you see in the numerator of your transfer function. Because if you will evaluate it, you will have that constant remaining. Now, this is the transfer function for liquid level systems. If we want to relate the head to the flow, changes in the flow, head is the level of the liquid inside the tank for a single tank system. You have this one as the transfer function. Your tau here, your time constant, is the product of the cross-sectional area of the tank, which should be constant, and the linear resistance to flow. Now, if we want to relate, on the other hand, the volumetric outflow, that's Q sub O, and to the changes in the inflow, that would be 1 over tau S plus 1. So there's something here. I will just have this edited class. This, by the way, should be written here. Your Q is equal, your Q sub O. Let me just write it in here. This should be written here. They just overlap. So your Q sub O, the volumetric flow rate through the linear resistance, is equal to the level of the liquid inside the tank divided by the linear resistance. So that one just plays in there. This Q sub O of S over Q of S is equal to 1 over tau S plus 1. Okay. That's it. Let me check what we have here next. So if your Q sub O is a pump, it's a constant outlet flow, the transfer function is even simpler. Okay? Head to changes in the volumetric inflow is just 1 over AS. For a mixing process, the transfer function relating the changes in the concentration, outlet concentration, this is changes in the concentration of the shall I say the system or the liquid that is introduced into your mixing chamber. So X is input, Y is output. Both of these are representing concentration. So the Laplace transform is comparable to the Laplace transform of a thermometer. Okay, same with the Laplace transform of a liquid level system when we relate outflow to the linear resistance to changes in the volumetric inflow. Okay, they have the same form in the transfer function. Here, your tau is the volume divided by the volumetric flow rate. The volume of the tank or the mixing chamber divided by the volumetric flow rate. Okay, we will continue this on Wednesday. I'll stop sharing for now. Do you have any concerns for now?